talk today by Onno Zoeter from Booking.com, who's in the process of setting up a new collaborative lab between Booking.com, Technical University Delft, and the University of Amsterdam. So if you're online, hey Onno, good to see you.
Good evening, Martin.
Welcome.
What I would like to do is introduce the Mercury Machine Learning Lab, Mercury being the Roman god of travelers, among many other things. And one major theme in that lab, which is learning from controlled sources, which is a very exciting field of research that is in need for, say, a new name. I'm using this one for the moment. So you can go to the next slide. What I'll do, to give you an idea of what I'm talking about, I'll present 3 examples. And since you're all smart people, you can also take them as challenges. And so the first one is a simple, say, it could be a medical application, where in a hospital, there are many things that are measured at the patient. These are inputs, XI, and outputs are the recovery of the patient. And for this simplified example, assume that that's a binary thing. It's a yes-no thing. And it's measured. And so the hospital has years worth of this data. It's very valuable, and it aims to build a model. So P of Y given X, the probability of the patient recovering given what is measured at the moment. And it does that in solid fashion. So it takes the data that it has and it separates it in training data and test held out data. And lo and behold, the model that they've trained on the training data, it predicts well on this held out test data. So it looks like what is measured at the patient level is quite predictive on this recovery. But now when this model is actually put to use, something interesting is happening. So the doctors now get access to the model predictions when they make the rounds, when they interact with patients. And when the model predicts a low probability of recovery, they intervene. And luckily, they're often successful. But now with that success, the predictions of the model have become inaccurate. So that's an interesting thing, that the model is built, and by its own use, it is making itself basically incorrect. So that's example 1. If you can go to the next slide. This is in, let's say, a ranking scenario. So here, consider there's an e-commerce company. It's not Booking.com. And it is hosting a Kaggle competition. It has also a very valuable data set. In this case, it is the context, similar to presentation of the Elsevier lab, X sub I, where in the context, a particular list of items that needs to be clicked or bought or whatever the discrete event is that we're interested in. And then the final buying or clicking, whatever discrete event, again, let's say buying signals. And what they do, they take, say, 80% of that data, they give it to the community of teams that might be interested in participating in the competition. And these teams are asked to create an algorithm that, given a context, will create a ranked list. And the scoring is now, it's on this 20 data that the company has held back as an evaluation or as a test set. Each algorithm is given a context, creates a ranked list. And now because the held data is from the past, the actual buying decisions are monitored, they're observed. And so the higher that bought item is put in the list, the higher the score. Right? And so how this is weighted and summed over different pages can be done in different ways, so NECG or MRR, and these details are not important for this example. And again, here the outcome is surprising. So this company thought that their current ranker that they had in production was not that good, actually. Actually, they knew that there was a very important product category that ranker was missing completely. Yet, the winning submission was very, very similar to the ranker that they were currently using. And so that puzzled them. So you can go to the next slide and we can look at the third and final example. This could be, say, a stylized bank scenario. So, and this actually, fun fact, this is a paper that was discussed in my very first machine learning course in 1995. So this goes in a scenario where the bank was using human assessors to decide to accept or not accept an application for a credit card. And so applicants would come into a physical bank office, and they would have filled out an application form, and they might have, in background credit scores, so things that we could measure about the applicant, X sub I. And the human assessors, they would physically talk to these people. They might actually have an light interview, ask questions. And the task for the human assessors is to figure out if the applicant will likely pay back all their loans, or might default, might go bankrupt and not pay back their loan, which is a costly event for the bank. So, and again, the bank here has a very valuable data set. It now has years of data of these inputs, the filled out application forms and credit scores, and then the course of events for these applicants when they get a credit card, if they pay back their loans or go bankrupt, and making this a very costly customer for the bank. And so the bank is figuring, well, the human assessors, that's a time-consuming task and it is costly. We now have this data, so we can build a model and use that instead. It will be faster, it will be cheaper. And again, on held out data, this model performs very well. But when it is actually put in use, so now the human assessors are put on other tasks and the model is performing their task instead, the defaults are a lot higher than predicted. And in fact, when the people inspect the model that was trained, there was something counterintuitive. If people would come in and in their form, they had ticked a box that they had defaulted in the past, so going from not going default in the past to default in the past, the predicted probability of going defaulting on the credit card would actually go down. It was counterintuitive. So if you can go to the next slide, I want to make a claim here based on just these 3 examples, but I could have put many, many more. The classic supervised learning problem that we get taught in our Machine Learning 101, and that is the topic of Kaggle competitions, is not rich enough to capture the real world problems that we see when we apply machine learning problems, or very many of them we don't. And if we now go to the next slide, so we can now go over these 3 examples and say what was going on, right? If it would be a live event, you can, interactively, you could test yourself, but let me just, in this setting, just go through them. So in the medical application, the data, so yes, there's years worth of data, but the data reflects, partially the physiology of the patients, but also the effects of the standard, say the default treatment of the doctors in the hospital. And now when the model is put in use, say alarming predictions leads the doctors to deviate from their standard policy. And so actually our modeling obligation is not just to predict what is happening under the treatment policy that was, say, the default during the years that the data was gathered, but you'd want to predict as a function of the policy, right? And initially, when we do this, the method needs to also be rich enough to understand when it is stepping into areas where it has very little data. So that is what is going on in the first example. And then if we go to the next slide, then we can look again at the ranking. So the ranking problem, what is obviously going wrong here is the position effect of items. So what customers buy in an e-commerce store is a function of how good the items match with the intent and the desires of the customer, but also how prominently they're shown. In the extreme example, if they're not shown at all, they can't be bought. And the training data, and in particular the test data on which these different candidate algorithms are scored, this data is generated by the previous ranker. And so the things that are bought a lot are the things that are shown prominently by the old ranker. In particular, if the old ranker, didn't show a very important category of items at all, a new ranker might be a significant improvement by correctly showing this category when relevant, but it will get 0 score for it using this scoring method, because in the held out test data, the buying events of these just don't happen. And so if we now go to the last example, the credit card story, here what is going on is that the human assessors, they have filtered out certain candidates, certain applicants. So they've applied for a credit card, but because the human assessors deemed them to be quite risky, they did not receive a credit card, and therefore they don't enter into the database. And more importantly, that the information that these human assessors use is the information on the form, credit score, but also the discussions that they might have with that applicant that don't make it into our digital database. And so what is going to happen is that a category of high-risk customers that weren't seen and were filtered out using different means now do get let through. That's why default goes up when the human assessors are replaced by the machine learning system. And if we want to understand of how it could be that defaulting in the past, going bankrupt in the past, how that might be favorable towards the predictions of not defaulting in the future, imagine that these human assessors, it's their task to figure out which customers pose a high risk and to make sure that they don't get a credit card. If they see that people have gone bankrupt in the past, that's of course a big red flag. And if they're extremely conservative, in other words, for customers that have gone bankrupt in the past, they need to come with a very solid story of why that was so and why that won't be repeated. If they're very conservative, it means that those customers that still after that interview make it through the database are ones that are on average less likely to go bankrupt, less likely to default. And so now I'd like to make a second claim. So we move to the next slide. So we've now seen three cases. We've seen three cases where the standard supervised learning problem of matched input-output pairs xi's, yi, and creating a conditional model P of y given x, why that's not rich enough, why that problem statement is not rich enough. We've gone through these three examples, and we have now, after the fact, in an ad hoc way, reasoned what went wrong. And so that's in some sense, it's satisfying. We think we probably can go about trying to fix some of these things. But my claim here is that there's definitely not generally accepted formalism in which these problems could have been framed, such as these problems, such that the surprises and say the mismatch between the construction of the model and its use, that doesn't happen. Right? And that is, of course, the thing that we hope to tackle in the Mercury Machine Learning Lab, in the Learning from Controlled Sources theme. So the idea is that when we look back in 5 years, that, say, for examples like we've seen today, that we have a practical, easy to use, reliable formalism in which we can state these problems, such that a ready set of algorithms can solve them, and that avoids the complications that we see in the examples here. And so why now? So if we go to the next slide, then there are several very nice shoulders to stand on already. So in this first presentation, also short presentation, I won't give you a very thorough overview of all the related literature, but I want to just highlight one as an example that this is, we don't start with a complete blank sheet of paper, and that's the notion of S recoverability. So if we now take the last example again, the bank application, which applicant to give a credit card to, let me refine the story a little bit. So this paper was a very old one where human assessors in a physical branch office generated data. If we would do it today, then probably a new algorithm would be relying on data that comes from the algorithm that ran before it, that was feeding off data that was just stored in a database. Now we ask ourselves, that sounds very, very related. Is there now a fundamental difference, yes or no, between these two scenarios? When we describe them in words, is there a difference, right? And is there a formalism in which we can reason about it? If you go to the next slide, then as recoverability by Barenboim and Pearl is an elegant formalism to reason about these things. So here we have the supervised learning problem, output y, input x. And what we do is we create another variable, a discrete variable s, which says, is this, will this entry be added to our database? Yes or no? The s variable discrete. And that's a function in the case that it's an algorithm looking at only digitally stored data x. It is represented in this graph for those people in the audience that know base nets. And now we have that the conditional distribution of y given x. So y is independent of s given x. So no matter if s is 1 selected or s is 0 not selected, it doesn't change the conditional relationship y given x that we try to learn. And so in this specific scenario, intuitively, initially you might think, well, we want to learn about how risky or how likely the event is that a customer will default on its loans. And in our data set, the highest risk customers have been pruned out. Your first reaction might be, so, well, that will include a bias. So now we can't learn reliably this relationship. But here, in these conditions, this graph shows that we can. And then the next slide, if you can switch to the next slide, is graphically an intuition. So suppose that x is just a single dimensional scalar, and say the ground truth is a logistic regression. So the probability of default, y being 1, given x is logistic regression. So the example on the left, the blue curve, and we would get data, this are the points. So some are 0, no default, some are 1, default. And now filtering means that beyond a certain level of x, so the red points, don't make it to our database. That means that we are blind to certain levels of x, but we have enough data to, in an unbiased way, fit the logistic regression curve. On the right, this is replicated very many times, and indeed you can see that the bias, so what is learned versus what is the ground truth from which it's generated, that's in expectation the same. So if you can go to the next slide. But if we now tweak the story a little bit and say we go back in the scenario where humans interact and they look at X, what is filled out in the application form and the credit scores, but next to that also to Z, say things that come up in a discussion that are very important in the selection, in deciding whether or not somebody gets a credit card, but it doesn't make it to the database. Now, all of a sudden, there is a distinct bias because now there is the high-risk customers that look to the same to the algorithm, looking only at X, now are filtered out by other features Z. And graphically, for those of you that know D separation, Y is now not independent of S anymore given X. So if we go to the next slide, next and last slide. To me, this is, and I've seen in many companies, important manifestations of these problems, where potentially very impactful application actually failed. This research field, we do hope that by the end of 5 years, standing on shoulders like the ones here, so recent advances in the field of causality, but also in information retrieval, reinforcement learning, looking at 3 separate fields, different points of view to the same problem, to in 5 years' time, looking back at these examples and have a clear formalism that would solve them. I'm very happy and honored to work with a very strong group of people at the University of Amsterdam with Joris Mooij and Maarten de Rijke, here present today, at Booking with Christina Casimiro, Hadi Rouhani, and in TU Delft with Frans Oliehoek and Matthijs Spaan. The other theme that I won't have time to go into today is also very interesting and exciting is natural language processing, where we'll be working with Wilker Aziz and Ivan Titov, and with Priyanka Agrawal at Booking.com. With that, on the final slide, thanks for your attention. If there are any questions, I would be very happy to answer them.
Thank you so much, Onno. We have a question by Arjan Vreken. Is one of the challenges to make these unobserved features explicit? And if so, how do you do that?
Interesting question. So the nice thing is if you're building a real world application, indeed, sometimes it can be that to improve that real world system or to get the best increase in increase in impact of your system is to go and record additional things, add additional sensors, force people to record things, force them to interact only through things that you can log and store. So yeah, in very many practical applications, it could very well be that's the best thing to do. But from an academic point of view, the need for a formalism to write down and be very specific about what is observed, what is not, what are the implications of it. I think there will just always be cases where you can't prevent things to go unobserved. So the formalism and the algorithms should be ready to handle cases where these things are not observed. And then the most important thing is to, the default assumption is that there are no unobserved things that make things difficult, which is a very dangerous one to make. So can we build systems that make less weight to that default assumption, or at least help us alert if these assumptions seem to be improbable. That answers the question. Otherwise, please add a follow-up one. Could you apply it to HR processes such as recruiting? My experience is that indeed with all these things where you tend to make decisions, and so there could be a very strong overlap with the presentations we've seen before, so with fairness and all these things. My experience is that these things very often pop up. And so if you're building a machine learning application in HR processes, it makes very solid sense to take a coffee and to see which of these issues, variants of these issues might apply to you. And indeed, we hope that we can then make it easier for you to identify these things and come with a set of practical algorithms for you to help. But short answer, probably yes. We'll have to look at the details to figure out which ones.
So there's a next question by Radu. Can you say if the, I'm not sure whether this should be S measures or simply measures in some way.
Yeah, maybe the S discoverability.
Yes, the S from your graphs.
Measures.
Yes. Yeah. Measures in some way the selection bias or sampling bias in the input data.
Yeah. So in this case, it's the sampling bias is a selection bias. So the samples that make it to our database are input-output pairs of customers that made it through the screening process of the human assessors in the bank example. And as recoverability in general asks the question, if we want to learn a conditional probability of y given x, and we know that some of the samples were filtered out and didn't make it to our database, under which conditions can we correct for that? And can we still retrieve this conditional distribution of P of y given x? And in the bank example, it trivially holds. In richer settings, you might need to try to reuse other pieces of data and correct for the bias. So it's the S discoverability tries to answer the question how, if and how you can correct for the sampling bias that comes from selection bias. Yeah.
Thank you, Onno. And in the case of the ranker example, would that be you need to keep a record of what policy was used to collect the interaction data?
So in the ranking example, I think to explain an item that is bought or not is a function of how well that item matches to the intent and the desires of the customers as expressed through the context,
yeah,
and how prominently the item was shown. So you need to include in your one way to go about it. I'm not saying it's the only one, but one way to go about it is to change the competition, to not ask for a complete ranked list, but to say, I'm not only going to give you the context, I'm going to give you the context and the list that was shown to by our old ranker. Tell me what's going to happen. Tell me what is going to be booked. And now, if you can do that well, if you have a model that predicts that very, very well, and now you say, well, the most likely thing that will be bought is at position 10 instead of position 1, then you can also say, okay, what would happen if we would swap it around and we would put the item that's at position 10 and put it at position 1. So if you then trust your model, you can use it to optimize your ranked result list. And so the challenge to the model should then be not give us a ranked list, but be as accurate as possible in predicting what's going to happen given context and what the old ranker decided to show. And then the position effect is, say, analogous to the unobserved information that was withheld in the banking documents.
Yeah. Okay, thank you, Onno, both for the presentation. Maybe one last question. So the lab is in the startup phase now. Recruiting is happening. Can you share a bit of the timeline that you have in mind?
So we're very happy to report that the first students have accepted our offers and will start this year still. We think the majority of the students and postdocs will join us in the first quarter next year. And then there will be a phase, it will be new for booking as well. So we have celebrated our 25th, we're celebrating our 25th birthday, but it is relatively new engaging with academic groups. So we'll use, I think, the first half year, so for all students to ramp up in their respective fields, and for the teams in booking to start engaging and on both sides to learn how that works best. So I am very convinced that there are very useful lessons to learn, even for academics, professors, and students that have an ambition to, after that, only do theoretical work, but to just say sharpen the mathematical abstraction of the problem, but also just get feedback from empirical, what works, what doesn't work. And we will need to go and be conscious of the fact that we need to learn what the best ways are in engaging to capitalize on that opportunity. So both for the people at the university and people at Booking.com. But I'm very convinced, because there's so much great stuff to be done that they will get to great things quite quickly also. Yeah.
Okay, looking forward to it.
Thanks a lot. Thanks everyone. Thanks for staying away from your dinner and drinks. And, hope to report back once we're a little bit further on in the lab.
Okay, we'll be sure to invite you again.
Yeah.